a red giant 650 light-years away is acting up, and the scientists watching it are losing sleep. Betelgeuse, the star on Orion's shoulder, is so massive that more than 400 million suns could fit inside it. Now it's pulsing in ways nobody predicted, hiding a secret companion in its atmosphere, and burning through the last fuel it will ever have. Tonight, we'll go inside the dying giant, meet the hidden star called Siwaha, and find out why some astronomers believe the explosion could happen in our lifetime. If cosmic mysteries pull you in, hit subscribe and stay close. Prepare yourselves. We begin. There's a star in the sky right now that telescopes around the world refuse to look away from. Every clear night, observatories from Hawaii to Chile to the Canary Islands turn their lenses toward the same red dot in the constellation Orion. They are watching it the way a doctor watches a patient hooked up to monitors. Something is happening up there, and nobody is willing to miss the moment it ends. The star is called Betelgeuse. You have probably seen it without knowing, that orange-red glow on the upper left of Orion the Hunter, marking his right shoulder. To the naked eye it looks ordinary, just one bright point among thousands. But Betelgeuse is anything but ordinary. It's a red supergiant in the final act of its life, and the way it has been behaving over the past few years has astronomers genuinely rattled. The trouble started in late 2019. Betelgeuse began dimming, not a little. The star dropped to about 40% of its normal brightness, enough that anyone glancing at Orion could tell something was wrong. People started whispering the word that always hovers around this star: supernova. For a few weeks, scientists wondered if humanity was about to witness the closest stellar explosion in recorded history. Then it brightened again. The panic faded. The dust cloud theory took over. The story moved on. But the star did not stop misbehaving. In the years since, Betelgeuse has continued to pulse in strange rhythms, swelling and shrinking on cycles of 185 days, 230 days, 420 days, and an unusually long cycle that stretches across roughly 2,100 days. These rhythms overlap and collide, creating a pattern that has refused to fit the standard models of how a red supergiant should age. Then in 2025, astronomers confirmed something even stranger. Betelgeuse is not alone. It has a small companion star tucked so close that the larger star's atmosphere actually swallows it during part of every orbit. They named the companion Siwaha, and the discovery rewrote almost everything we thought we knew about why Betelgeuse has been acting so unstable. Here is what makes the watching so urgent. A star this size, this old, this close to Earth, is exactly the kind of star that goes supernova. When it does, the explosion will be the brightest thing in the night sky for months. It will be visible during the day, it will outshine the full moon. And the light that finally reaches us has been travelling for 6.5 centuries, which means the explosion may have already happened in real time. The flash could arrive tonight. Or in 50 years. Or in 50,000. The honest answer, the one most astronomers will give if you press them, is that they don't know. The star's behaviour right now does not fit any single neat prediction. Some teams argue it could blow within decades. Others insist it has many thousands of years left. Both sides are reading the same data and reaching opposite conclusions, which is rare in modern astronomy. That uncertainty is exactly why nobody is looking away. Because if Betelgeuse does go, the warning signs will appear first in the data, hours or even days before the human eye sees anything, and those signs may already be starting to show. Step outside on a clear winter night and look south. If you live anywhere in the northern half of the world, you will find one of the easiest constellations in the sky. 3 bright stars in a perfect short row, evenly spaced, almost a straight line. That's Orion's belt. Once you see it, the rest of the constellation falls into place around it like a giant hourglass. Above the belt, on the upper left, there's a star that glows differently from the others. Where most stars look white or bluish, this one carries a clear orange tint. That's Betelgeuse. Hold your hand at arm's length, spread your fingers, and the star sits roughly the width of your palm above and to the left of the belt. Below and to the right, you'll spot another bright star called ridddle, glowing icy blue. The contrast between the two is striking once you know to look for it. Orion is one of the oldest constellations in human history. Ancient Egyptians saw the god Osiris in those stars. The Greeks turned the figure into a hunter raising his club against Taurus the bull. Almost every culture on Earth recognized the same human shape in this patch of sky. And almost every culture noticed Betelgeuse glowing red on his shoulder, because the red colour stands out so clearly against the cool blue of ridddle and the white hot stars of the belt. The name itself is a puzzle. Most likely it comes from an old Arabic phrase that was misread by medieval translators, eventually corrupted into the version we use today. The original name probably referred to the hand or shoulder of the giant. Whatever the original meaning, the name has stuck for nearly 1,000 years, and it now belongs to one of the most studied stars in the sky. Here is the thing about looking at Betelgeuse with your own eyes. The light hitting your retina right now left the star around the year 1375. While that light was travelling, the Black Death was sweeping through Europe, the Ming dynasty was just beginning in China, and the Aztecs had not yet built their great city. By the time those photons crossed the gulf between Betelgeuse and Earth, 6.5 centuries of human history played out. Every glance at the star is a glance into the deep past. That distance matters for another reason. Betelgeuse sits about 650 light-years away, which sounds enormous, and by human standards it is. But on the scale of our galaxy, that's practically next door. The Milky Way stretches roughly 100,000 light-years across. Betelgeuse is in our cosmic neighbourhood, close enough that we can resolve features on its surface, close enough that when it explodes, the light show will dominate Earth's sky for months. You can watch Betelgeuse change with the naked eye. Most stars hold steady. This one wobbles. Over weeks and months, careful observers can see the brightness shift, sometimes dramatically. During the Great Dimming, anyone who looked up could tell Betelgeuse was fading. That's almost unheard of for a star, especially one this famous. So next time you're outside on a clear night, find the belt, follow it up to the orange shoulder, and pause. You're staring at a doomed giant, and you're seeing it as it was hundreds of years ago. What's happening up there right now is something we won't witness for centuries. Unless, of course, the explosion already happened. Try this thought experiment. Picture our sun, the bright disk that warms your skin in summer. Now picture our entire solar system: Mercury, Venus, Earth, Mars, the asteroid belt, and Jupiter way out past the gap. From the Sun to Jupiter is a distance of roughly 480 million miles. Light from the Sun takes about 43 minutes to reach Jupiter. That's a lot of empty space. Now scoop up the Sun and replace it with Betelgeuse. The new star is so enormous that its surface would extend past the orbit of Mars, past the asteroid belt, all the way out to where Jupiter currently swings through its lonely orbit. Earth, the Moon, all our inner planets would be deep inside the star, vaporized in an instant. Jupiter itself would be skimming the boiling outer layers of Betelgeuse's atmosphere. The numbers behind this are almost impossible to feel. Betelgeuse has a radius somewhere between 640 and 764 times the radius of the Sun. Estimates vary depending on how astronomers measure the fuzzy edge of the star, because Betelgeuse doesn't really have a sharp surface the way Earth has a sharp coastline. The atmosphere just keeps thinning out into space, layer after layer, until eventually you can't tell where the star ends and the void begins. If you tried to fly an aeroplane around Betelgeuse at cruising speed, the trip would take more than 1,000 years. If you wanted to compare volumes, more than 400 million suns could fit inside Betelgeuse with room to spare. That sounds like an exaggeration, but the math is real. The star is that big. Here's the strange part. Despite being unimaginably huge, Betelgeuse is not particularly dense. The outer layers are thinner than the air you're breathing right now, much thinner. If you could somehow stand inside the upper atmosphere of Betelgeuse and survive the heat, the gas around you would be closer to a laboratory vacuum than to anything we'd call a fluid. The star is bloated, puffed up, inflated to the point of being almost a glowing fog. That bloating is a sign of what's happening inside. When stars get this large, it means their cores have changed dramatically. The fuel they were born with is mostly used up. They've moved on to burning heavier elements, and as the core compresses and heats up, the outer layers respond by expanding outward. The star essentially turns inside out over the final stages of its life. Betelgeuse has expanded so much that its surface gravity is weaker than the gravity of a small asteroid. This is why the star pulses. The outer layers are so loosely held that small disturbances inside the core ripple all the way out, swelling the star and shrinking it on cycles that last hundreds or thousands of days. Every pulse is a reminder that Betelgeuse is a balloon barely holding itself together, and the size keeps growing. As the star burns through heavier elements, it will swell further before the end. The final radius, just before the supernova, will be even larger than what we see today. The atmosphere is already so vast that a small companion star can orbit inside it. Which brings us to the strangest discovery of all about this giant. There is something hiding in there with it, and it has been hiding for a very long time. Size and mass are two completely different things, and Betelgeuse proves it. The star is large enough to swallow most of our solar system, but its mass tells a more focused story. Best current estimates put Betelgeuse at about 16 to 20 times the mass of the Sun. That sounds modest compared to the volume, but in stellar terms it is the dividing line between two completely different fates. Stars below about 8 solar masses end their lives quietly. They puff off their outer layers in slow exhalations, leaving behind small hot cores called white dwarfs that cool over billions of years. Our Sun will follow that path eventually, fading into a quiet ember. Stars above 8 solar masses do something else entirely. They explode. There's no calm exit, no gentle fade. The mass is too great for the core to settle into a peaceful retirement. When the fuel runs out, the core collapses in less than a second, and the star blows itself apart in a supernova that briefly outshines entire galaxies. Betelgeuse is comfortably above this threshold. It cannot avoid exploding. It is only a matter of when. This is what makes the mass measurement so important. If Betelgeuse was smaller, the conversation would be different. We'd be discussing a slow stellar retirement, maybe a beautiful planetary nebula, but not a galactic scale event. Because the star is roughly 16 suns, the ending is locked in. Physics will not allow anything else. Mass also controls how quickly a massive star burns through its life. Stars are like cars. Bigger engines burn fuel faster. Our Sun has been on the main sequence, fusing hydrogen into helium, for about 4.5 billion years, and it has another 5 billion to go. Betelgeuse, by contrast, is only about 10 million years old. That's it. 10 million years from birth to the brink of explosion. In that same span of time, our Sun would have barely noticed it had aged. Inside Betelgeuse, the mass is doing something violent right now. The core is burning carbon, fusing it into heavier elements like neon and magnesium. The hydrogen ran out long ago. The helium ran out after that. Each new fuel burns hotter and faster than the last, and each stage gets dramatically shorter. Hydrogen burning lasted millions of years. Helium burning lasted hundreds of thousands. Carbon burning lasts only about 1,000 years. The next stage after carbon, neon burning, lasts maybe a single year. Oxygen burning lasts a few months. Silicon burning, the final stage, lasts about a day. That sequence is almost impossible to internalize. A star that has lived for 10 million years will burn through its final fuel in 24 hours. The countdown shortens dramatically as the end approaches, and each stage leaves the core hotter, denser, and closer to the breaking point. By the time silicon burning starts, the supernova is essentially inevitable within hours, Right now, scientists believe Betelgeuse is somewhere in the carbon-burning phase. Some teams argue it's deep in that stage. Others say it just started. The difference between those two readings is the difference between an explosion in our lifetime and an explosion long after every person reading this is gone. The mass tells us the ending. The fuel tells us the timing, and right now, the timing is the part nobody can pin down with certainty. In October of 2019, observers around the world started noticing something odd. Betelgeuse looked dimmer than usual. At first the change was subtle, the kind of thing only seasoned amateur astronomers catch when they compare the star to its neighbours in Orion. But over the following weeks, the dimming accelerated. By December, the star had visibly faded. By February of 2020, Betelgeuse had dropped to roughly 40% of its normal brightness, the lowest level recorded in more than a century of careful observation. This was not a small fluctuation. Stargazers who had memorized Orion since childhood could see that something was wrong. The right shoulder of the Hunter looked dim and washed out. Ridddle, on the opposite side of the constellation, suddenly looked much brighter by comparison. The familiar shape of Orion was changing in real time, and astronomers around the planet pointed every available telescope at the star to figure out why. The internet did what the internet does. Within days, supernova rumours were everywhere. Headlines speculated that we might be about to witness the closest stellar explosion in recorded history. Articles described what the explosion would look like, how bright it would shine, whether it would be dangerous. The hashtag spread through social media. People who had never thought about stars before suddenly knew the name Betelgeuse. Some of the speculation was justified. Theoretical models had long suggested that red supergiants might dim noticeably in the months before they explode. The dimming could be caused by violent activity in the outer layers or by material being thrown off as the core destabilizes. If Betelgeuse really was preparing to blow, a sudden drop in brightness was exactly the kind of warning sign astronomers had predicted. But supernova was only one possible explanation, and most professional astronomers urged caution. Red supergiants are unstable by nature. They pulse. They flicker. They throw off material. A dimming event, even a dramatic one, was not enough on its own to declare the end was coming. The teams watching most closely wanted more data before drawing any conclusions. The Hubble Space Telescope was redirected to study the star in ultraviolet light. Ground-based observatories tracked the spectrum, the colour signature, the apparent shape of the star's surface. Images taken during the dimming showed something startling. Betelgeuse no longer looked round. The southern half of the star appeared much darker than the northern half, as if a giant shadow had fallen across the lower part of the disk. That asymmetric darkening was the key clue. A supernova precursor would not produce a one-sided shadow. Something was blocking light from reaching us, not weakening the star itself. The most likely culprit was a massive cloud of dust that had been ejected from the southern hemisphere of Betelgeuse, then cooled into the kind of opaque material that absorbs visible light. By April of 2020, Betelgeuse was rebrightening. By the end of the year, the star had returned to roughly its normal output. The dust cloud, whatever it was, had dispersed enough to let the light pass through again. The supernova fears faded, replaced by a new wave of curiosity about what had really happened. The great dimming had not been a death rattle. It was something stranger, and the explanation took years to fully untangle. The dust was real. But the dust was not the whole story. When astronomers finally pieced together the great dimming story, the picture that emerged was both simpler and weirder than anyone had expected. Betelgeuse had not started its death sequence. It had burped. In the months leading up to the dimming, the star had ejected an enormous mass of hot gas from its southern hemisphere. This kind of ejection is something red supergiants do regularly, although usually on smaller scales. Betelgeuse loses material constantly through what astronomers call stellar wind, basically a steady leak of atoms and dust streaming away from the surface. But this particular event was different. A huge plume of plasma was launched outward in a single burst. the plume travelled out into the cold space surrounding the star. As it cooled, the gas began to condense. Heavy elements like silicon, oxygen, and carbon clumped together into tiny grains of dust, similar to how steam in your bathroom condenses into water droplets on a cold mirror. Within months, the ejected material had transformed from an invisible cloud of gas into a dense screen of microscopic dust particles, perfectly positioned between Betelgeuse and Earth. That dust acted like a curtain. Visible light from the southern half of the star was absorbed and scattered by the grains, while the northern half continued shining normally. From our perspective, half of Betelgeuse simply went dark. The total brightness dropped by more than half. The star looked like it was failing. The asymmetric pattern in the Hubble images matched this story perfectly. Deep ultraviolet observations showed that the upper layers of Betelgeuse had cooled noticeably in the months before the dimming, exactly the kind of temperature drop you'd expect after a massive ejection of hot material. Spectra revealed the chemical fingerprint of fresh dust grains forming in the outer atmosphere. Every piece of evidence pointed to the same conclusion. The star had thrown off a chunk of itself, and that chunk had cooled into a dust cloud that blocked our view. So why did this happen? The triggering cause is still debated. Red supergiants have huge convection cells on their surfaces, regions hundreds of times larger than the entire Sun, where hot material rises and cooler material sinks. These cells are unstable. Sometimes a particularly large cell can rise so violently that it punches through the upper atmosphere and ejects material into space. Some teams think one of these massive cells was responsible for the Great Dimming. Other researchers suspect the pulsation cycles were involved. Several of the regular brightness rhythms happened to bottom out at roughly the same time in 2019, amplifying a normal dim cycle into something extreme. When the dust ejection landed on top of that natural minimum, the combined effect produced the deepest dimming in modern records. There's also the companion star theory, which emerged later. The presence of Suaha ploughing through the outer atmosphere of Betelgeuse may stir up the gas in unpredictable ways, encouraging eruptions and ejections that wouldn't otherwise happen. If Suaha was in a particular part of its orbit during the months before the dimming, the timing could matter. The Great Dimming taught astronomers something humbling. We thought we understood red supergiants reasonably well. We did not. The star was capable of behaviour that surprised everyone, and whatever we thought we knew needed revising. And the next surprise was already on its way. Most stars hold a steady glow. Look at them year after year and the brightness barely changes. Betelgeuse does not behave that way. The star pulses, it swells and shrinks, it brightens and dims on regular cycles that have been tracked for more than a century, and the pattern is much stranger than anyone expected. There are 4 main rhythms in Betelgeuse's brightness. The shortest is about 185 days. The next runs for 230 days. A third cycle stretches across roughly 420 days, which has been the most carefully studied period because it's the easiest to spot in long-term records. And then there's the strange one, a slow rhythm that takes about 2,100 days, almost 6 years from start to finish. These overlapping cycles are what make Betelgeuse so visually dynamic. Sometimes 2 or 3 of the rhythms hit their dim phases at the same time, and the star fades noticeably. Sometimes they peak together, and Betelgeuse looks unusually bright. Most of the time the cycles partially cancel each other out, and the star wavers in patterns that take careful tracking to predict. For a long time, astronomers debated what was producing each rhythm. Stellar pulsations seemed like the obvious answer for at least some of them. Massive stars near the end of their lives are known to pulse, with their outer layers swelling outward and then falling back inward like a gigantic, slow heartbeat. The driving mechanism is a delicate balance between gravity, gas pressure, and the way the outer layers absorb and release radiation. When the balance tips one way, the star expands. When it tips back, the star contracts. The shorter periods, especially the 420-day cycle, fit this pulsation picture beautifully. The star's outer layers are physically rising and falling on these timescales. When the layers expand, they cool and dim slightly, When they contract, they heat up and brighten. The pattern is regular enough that astronomers can predict when the next bright peak or dim trough will arrive, but the 2,100-day rhythm did not fit. It was too slow to be a normal pulsation in a star of Betelgeuse's size. The physics simply didn't work. The longer the period, the harder it became to explain through pulsation alone. So researchers started calling this one the long secondary period, a placeholder name that essentially meant we have no idea what's causing this. Various theories tried to explain the long rhythm. Maybe huge convection cells were rotating across the star's surface, brightening and dimming the visible face on a long cycle. Maybe a magnetic activity cycle, similar to the 11-year sunspot cycle on our Sun but on a different scale, was responsible. Maybe a giant dust cloud was orbiting Betelgeuse, periodically blocking light from our view. Each theory had problems. None of them quite worked. There was another possibility, the one that had been whispered about for years without much evidence to back it up. What if Betelgeuse had a companion star? A small object orbiting the giant once every 6 years could pull on the gas, stir up the atmosphere, and produce the long periodic pattern that nothing else could explain. For decades, the companion star idea was a fringe theory. Most astronomers thought it was unlikely. The required orbit was inside the outer atmosphere of Betelgeuse itself, which seemed almost impossible. A star surviving inside the puffy envelope of a red supergent felt like a contradiction. In 2025, the contradiction became real. The hidden star was found. The 2,100-day cycle haunted Betelgeuse research for decades. No matter how many explanations astronomers tried, something always failed to fit. The rhythm was too steady to be random surface activity, too long to be a pulsation, and too consistent to be a passing dust cloud. Every careful study deepened the puzzle instead of solving it. Part of the problem was that nothing in Betelgeuse's known structure could naturally produce a 6-year cycle. The star's pulsation modes had been calculated with great precision by stellar physicists. The math allowed for cycles of a few hundred days. It did not allow for cycles of 2,000 days or more. Whatever was driving the long period had to come from somewhere outside the standard pulsation framework. Magnetic activity was one of the leading candidates for years. The Sun has an 11-year cycle of sunspots and magnetic storms, driven by the way the solar magnetic field tangles and untangles itself. If Betelgeuse had something similar, perhaps on a 6-year scale, it could produce regular brightness changes as different regions of the surface became more or less active. The problem was that Betelgeuse showed no clear evidence of strong magnetic activity in the right pattern. Magnetic models could be tweaked to fit the data, but they always required assumptions that felt forced. Convection was another candidate. The surface of a red supergent is dominated by enormous convection cells, hundreds of times larger than the entire Sun, each one a churning plume of hot gas rising from below. These cells are visible. Telescopes have actually photographed bright and dark patches on Betelgeuse's surface that correspond to these massive convection structures. If the cells took 6 years to rotate around the star, or to evolve through their life cycle, they could in principle drive the long brightness rhythm. But the convection theory had its own troubles. The cells don't rotate uniformly. They form, last for some period, dissolve, and new ones grow in their place. Getting that chaotic process to produce a clean, repeating 6-year signal that stayed locked in phase across decades was difficult to justify. The math kept refusing to cooperate. Then there was the dust idea. What if a thick cloud of dust orbited Betelgeuse at just the right distance, periodically passing in front of the star and dimming it on a 6-year schedule? The geometry could be made to work, but it required the cloud to remain stable for many orbits, which seemed unlikely. Dust around a red supergent tends to disperse quickly under the pressure of the star's intense radiation. A single cloud lasting through dozens of cycles would be exceptional. Throughout all of this, a quieter idea kept reappearing in the research papers. What if there was a companion star? An object of perhaps 1 or 2 solar masses, orbiting Betelgeuse at a distance of a few astronomical units, would have a roughly 6-year period. As the companion moved through the outer atmosphere of Betelgeuse, it would drag gas behind it, brighten the surrounding region, and produce exactly the kind of long rhythmic signal that was being observed. The companion star theory had supporters going back decades, but it lacked direct evidence. No telescope had ever spotted a second light source near Betelgeuse. The supergiant's glare was so overwhelming that anything small enough to fit inside the orbit would be drowned out. For years, the companion remained a hypothesis that some astronomers believed and others dismissed. The data was hiding the truth in plain sight. It just took 8 years of patient observation to extract it. In 2025, a team of astronomers at the Centre for Astrophysics in Cambridge announced something remarkable. They had finally found it. The companion star was real. Hubble Space Telescope data, combined with observations from ground-based observatories, revealed the unmistakable signature of a small object orbiting deep inside Betelgeuse's atmosphere. The team named the companion Siwaha, an Arabic word that fits the historical naming tradition of the giant star. Siwaha is small by stellar standards. Best estimates put its mass at about 1.5 times the mass of the Sun, which is roughly average for a star, but tiny next to Betelgeuse. The two objects have a mass ratio of more than 10 to 1. If Betelgeuse is a beach ball, Siwaha is a marble. And the marble has been swinging around inside the beach ball's outer fluff for a very long time. The orbit is tight. Siwaha completes a full circuit around Betelgeuse every 5.5 to 6 years, which exactly matches the mysterious 2,100-day rhythm that had puzzled astronomers for decades. The orbital distance is roughly 4 astronomical units, similar to the distance between our Sun and the asteroid belt. In our solar system, that orbit would not even reach Jupiter. Around Betelgeuse, it places Siwaha well inside the outer atmosphere of the giant. Think about what that means. Siwaha is not orbiting alongside Betelgeuse, the way a planet orbits a star. The smaller star is partly embedded inside the larger star. It ploughs through the puffy outer envelope of Betelgeuse during every orbit, like a fish swimming through a cloud of glowing fog. The atmosphere of the giant is thin enough at that distance that Siwaha can survive the encounter, but not without consequences. Both stars are being affected by the contact in ways that astronomers are only beginning to map. The discovery solved several mysteries at once. The long brightness cycle now had a clean explanation. Siwaha's orbit was pulling gas around with it, creating a rotating asymmetry in Betelgeuse's atmosphere that brightened and dimmed the visible disk on a 6-year schedule. The shape of the cycle, the timing of the peaks and troughs, the slight irregularities, all of it matched what an orbiting companion would produce. The discovery also explained some of Betelgeuse's other strange behaviours: periodic bursts of brightness, asymmetries in the outer atmosphere, unusual shifts in the spectrum. Things that had been chalked up to chaotic surface activity now had a tidy mechanism. Siwaha was stirring the pot, and the pot was a star. Andrea Dupree, the lead astronomer at the Centre for Astrophysics on the Discovery team, described the moment as a front-row seat to watching a giant star evolve. Researchers had argued for years that an undetected companion might exist. The proof, when it finally arrived, came from 8 years of patient data collection. No single observation revealed Siwaha. The companion's existence emerged from the accumulated pattern, the way a faint signal slowly rises out of noise when you stack enough measurements together. There's one detail that makes this discovery feel especially urgent. Siwaha is currently behind Betelgeuse from our perspective, blocked from view by the giant itself. The companion is expected to swing back into visibility in 2027. When it does, astronomers around the world will be watching. The next 2 years are going to be busy. The clearest evidence for Siwaha's existence came from something called a wake. Not a wake in the funeral sense. A wake in the boat sense, the trail of disturbed water that follows behind a vessel, cutting through a calm surface. As Siwaha ploughs through Betelgeuse's outer atmosphere on every orbit, the small star drags gas along with it, leaving a long trail of denser, faster-moving material in its path. This wake is what telescopes finally detected. The team led by Andrea Dupree spent nearly 8 years tracking subtle changes in Betelgeuse's spectrum, the rainbow signature of light that reveals the speed, density and composition of the gas in the star's atmosphere. They were looking for repeating patterns that matched what a companion star's wake should produce. The patterns showed up exactly on schedule every time Sawaha completed another orbit. The wake appears just after Sawaha crosses in front of Betelgeuse from our viewpoint, which happens once every 6 years or so. As the smaller star moves through the giant's outer atmosphere, the gas is compressed in front of it and trails behind it like a comet's tail. From Earth, we see this trail as a distinct shift in the spectrum, a fingerprint of denser, more energetic material moving in a specific direction. The pattern matched theoretical predictions almost perfectly. The Hubble Space Telescope provided the most precise data. Its ultraviolet observations could resolve features in Betelgeuse's atmosphere that ground-based telescopes simply cannot see, partly because Earth's atmosphere absorbs most of the relevant ultraviolet wavelengths before they reach the surface. From its orbit above the atmosphere, Hubble had a clear view of the upper layers of Betelgeuse, where the wake was most visible. 8 years of careful monitoring produced the dataset that finally clinched the case. Ground-based observatories played a critical supporting role. Telescopes at the Fred Lawrence Whipple Observatory in Arizona and the Roque de los Muchachos Observatory in the Canary Islands provided continuous coverage that filled in the gaps between Hubble observations. The combined dataset spanned years of orbital motion, capturing multiple complete cycles of Sawaha's path through Betelgeuse's atmosphere. What the wake reveals is more than just the existence of a companion star. It reveals the dynamics of how a giant star's atmosphere responds to being stirred. The trail is not steady, it changes shape over time, evolves as it disperses, and interacts with other features in Betelgeuse's complicated outer layers. Each orbit of Sawaha leaves a slightly different wake, and tracking those differences is teaching astronomers things about red supergiant atmospheres that no other observation could provide. The wake also has implications for how Betelgeuse will eventually die. The companion is not a passive observer. By repeatedly ploughing through the outer atmosphere, Sawaha is actively shaping the structure of the gas around the giant. It's churning material, redistributing mass, and possibly affecting how the star sheds its outer layers in the lead-up to the supernova. When Betelgeuse finally explodes, the explosion will not be perfectly symmetric. The asymmetries, the irregular distribution of debris, the lopsided shape of the resulting supernova remnant will carry the fingerprint of Sawaha's long influence. Studying the wake is, in a way, studying the future of the explosion. The patterns left in the gas now are the seeds of the patterns we will eventually see in the blast wave, and every orbit refines the picture a little further. For astronomers, this is a once-in-history opportunity. No other red supergent in the sky offers this kind of detailed view. Betelgeuse, because of its closeness, has become a laboratory for studying processes that are normally invisible. The Sawaha discovery did not come from a single dramatic moment of insight. It came from years of patient watching. The team behind it spent the better part of a decade collecting data, refining models, and slowly building a case that could not be dismissed. The story of how that work was done says a lot about how modern astronomy actually operates. The Hubble Space Telescope has been in orbit since 1990. By the time the Betelgeuse companion search began in earnest, Hubble had already been working for more than 3 decades. Its ultraviolet sensitivity made it the only telescope capable of resolving the faint signals the team needed to track. Ground-based telescopes could record visible light from Betelgeuse with great precision, but the key fingerprints of Sawaha's wake were hidden in ultraviolet wavelengths that never reached the ground. Getting time on Hubble is not easy. The telescope is shared among hundreds of research teams around the world, and observation requests vastly outnumber available slots. The Betelgeuse team had to make repeated proposals, arguing that their data collection deserved priority. Each successful proposal earned them another batch of observing hours, which they used to capture Betelgeuse's spectrum at carefully chosen points in Sawaha's orbit. The orbital period mattered enormously for the observation strategy. Because Suaha takes about 6 years to complete one circuit, the team had to plan their observations across multiple full orbits to confirm that the patterns were real and repeating. A single pass would not be enough. Skeptics could always argue that any single signal might be noise or coincidence. Only by demonstrating that the same wake reappeared on schedule year after year could the team make the case unassailable. Ground-based observatories filled in the spaces between Hubble observations. The Fred Lawrence Whipple Observatory in Arizona and the Roque de los Muchachos Observatory in the Canary Islands ran continuous monitoring programs, tracking Betelgeuse's brightness and visible spectrum night after night. These observations could not see the ultraviolet wake directly, but they captured the broader context of how Betelgeuse's atmosphere was behaving at every point in Suwarah's orbit. The team also pulled in archival data. Betelgeuse has been observed by professional astronomers for more than a century, and amateur astronomers have tracked its brightness for even longer. Some of the earliest reliable measurements go back to the late 1800s. By combining historical records with modern data, the team could test their model against more than a century of behaviour, looking for the same 6-year rhythm in old observations that they were finding in new ones. The pattern held up. The 2,100-day cycle was visible in records going back generations, exactly as a companion star's orbit should be. It had been hiding in the data the whole time, waiting for someone to recognise what it was. When the team finally announced the discovery, the response from the astronomical community was a mix of excitement and careful scepticism. Several other groups around the world began their own searches, looking for independent confirmation. Within months, multiple teams had found the same wake in their own data, using different telescopes and different analysis methods. The discovery was solid. Andrea Dupree, who led the original team, described the moment as the long-suspected companion finally giving us a front-row seat to watch how a giant star evolves. The wake was the proof. 8 years of patient observation had paid off in a result that rewrote our understanding of one of the most famous stars in the sky. The discovery of Suaha is not just a fascinating curiosity, it changes the calculation for when and how Betelgeuse will eventually explode. A red supergiant with a companion star is a different kind of object from a red supergiant alone, and the timeline to the supernova is influenced by everything the companion does. The most immediate question is whether the two stars will merge before Betelgeuse explodes. Suaha is currently orbiting at a distance of about 4 astronomical units, but that distance is not necessarily stable. The companion is ploughing through the outer atmosphere of the giant on every orbit, and that motion creates drag. The same way air resistance slows down a moving airplane, the friction of pushing through Betelgeuse's gas slowly bleeds energy out of Suaha's orbit. Over time, the orbit shrinks. The companion spirals inward. Researchers studying the system have suggested that Suaha is being pulled closer to Betelgeuse by exactly this kind of orbital decay. The rate is hard to measure precisely, but the trend is real. At some point, the spiral will become a plunge, and Suaha will fall directly into the giant. The two stars will merge. If the merger happens before the supernova, the consequences are dramatic. A smaller star plunging into a red supergiant would deliver a massive amount of energy and angular momentum to the bigger star. Betelgeuse's outer layers would be spun up. Material would be flung off in a violent burst, brightening the system temporarily and reshaping the atmosphere. The merger event itself might be visible from Earth as an unusual brightening, possibly mistaken for the early stages of the supernova. This kind of merger scenario is exactly what some theorists suspect happened to other red supergiants in the past. Strange behaviour in similar stars, including the unusual rotation rates of some red supergiants, has long puzzled astronomers. A history of stellar mergers could explain those oddities. Watching Suaha and Betelgeuse approach each other gives us a chance to test whether the merger explanation is right. There is another possibility. The supernova could happen first, before Suaha has a chance to spiral all the way in. In that case, the companion would be caught in the explosion, and almost certainly destroyed. A small star sitting just a few astronomical units from a core collapse supernova would not survive the blast. Siwaha would be vaporized, its material added to the expanding debris cloud of the explosion. Either way, Siwaha is doomed. Whether it merges first or gets blown apart by the supernova, the end is the same. The companion will not outlive Betelgeuse. What this means for our understanding of the explosion timeline is more complicated. Some models suggest that the merger could accelerate Betelgeuse's evolution toward the supernova. Adding mass and angular momentum to a star that's already close to the breaking point could push it over the edge sooner than it would otherwise reach. Other models suggest the opposite, that the merger could temporarily stabilize the star and delay the explosion. Right now, nobody has a definitive answer. The presence of Siwaha is a new variable that astronomers are still working into their models. The timeline that existed before 2025 was based on a single star, Betelgeuse. The new timeline has to account for a binary system that may or may not merge before the supernova. Predictions are being revised in real time, and the uncertainty has gotten larger, not smaller. Right now, Siwaha is hidden. From our viewpoint on Earth, the small companion star is positioned behind Betelgeuse, blocked from direct observation by the bulk of the giant itself. Astronomers have been collecting data about the system, but they cannot see Siwaha directly during this part of its orbit. The companion is in eclipse, lost in the glare and shadow of its much larger partner. That will change in 2027. Based on careful calculations of Siwaha's orbit, the companion is expected to swing back into a visible position relative to Earth sometime that year. When it does, telescopes around the world will be ready and waiting. The reappearance is one of the most anticipated astronomical events on the calendar, and teams have been planning their observations for years. Why does this matter so much? Because no one has ever directly seen Siwaha. The discovery was made through indirect evidence, the wake the companion creates in Betelgeuse's atmosphere. The pattern of changes in spectrum and brightness clearly indicates an orbiting object, and the math works perfectly for a small star at the predicted distance. But seeing it is different from inferring it. Direct observation would be the final, unarguable confirmation that everyone is waiting for. The challenge will be enormous. Even at its most visible, Siwaha will sit close to Betelgeuse from Earth's perspective, and the giant's brightness will overwhelm the companion. Imagine trying to spot a candle held next to a stadium floodlight. The contrast is almost impossibly extreme. Astronomers will need to use special techniques to suppress Betelgeuse's light while preserving any faint signal from Siwaha next to it. One approach is called coronagraphy, named after the technique originally developed to study the Sun's outer atmosphere by blocking out the bright disk. A coronagraph creates an artificial eclipse inside the telescope, blocking the central star and revealing fainter objects around it. Modern space-based coronagraphs are sensitive enough to detect planets orbiting other stars. They should be able to spot a companion star that's much brighter than any planet, even right next to a giant like Betelgeuse. Another approach is interferometry, which combines light from multiple telescopes to achieve a sharper image than any single telescope could produce. Interferometric arrays have already resolved features on the surface of Betelgeuse itself, including bright and dark patches caused by convection cells. With careful timing during the 2027 window, interferometry might be able to pick out Siwaha as a distinct point of light separated from Betelgeuse's surface. The James Webb Space Telescope will likely play a role too. Webb's infrared sensitivity could detect Siwaha through the warm gas of Betelgeuse's atmosphere, possibly catching the companion's heat signature even if its visible light remains hidden. Multiple wavelengths give astronomers different ways to spot the same object, and the more confirmation routes the better. If the reappearance goes well, Siwaha's orbit will be measured with much higher precision than current estimates allow. Better orbit data means better mass estimates, better predictions of how fast the companion is spiraling inward, and better forecasts for when the merger or the supernova might happen. Every piece of new information sharpens the model. 2027 is also a chance to look for surprises. Maybe Siwaha is not exactly what we think it is. Maybe its mass is different from the current estimate. Maybe there's something unusual about its composition, or its surface, or its own behaviour as it interacts with Betelgeuse's atmosphere. The first direct observations could reveal new puzzles even as they answer old ones. The waiting room is crowded. In June of 2023, a team of researchers led by Hideyuki Sayo at Tohoku University in Japan published a paper that shook the Betelgeuse community. Their analysis of the star's pulsation cycles led to a striking conclusion. Betelgeuse, they argued, was not just in the carbon-burning phase of its life. It was in the late stage of carbon burning, possibly within a few decades of running out of fuel entirely. The implications were dramatic. If the team's interpretation was correct, Betelgeuse could explode within tens of years. Not thousands. Not even hundreds. Tens. People reading the paper might live to see the supernova happen. The argument hinged on a careful piece of stellar physics. Pulsating stars vibrate in different modes, similar to how a guitar string can vibrate at different frequencies depending on how you pluck it. The fundamental mode is the slowest, deepest oscillation. Higher overtones are faster, higher frequency vibrations. By identifying which observed period of Betelgeuse corresponds to the fundamental mode and which correspond to overtones, you can work backward to figure out what's happening inside the star. The Sayo team identified the long 2,100-day cycle as the radial fundamental mode, with the shorter periods, 420 days, 230 days, and 185 days, as the first, second, and third overtones. When they ran this assumption through pulsation models, they found that all four periods could only be excited together in a star at a specific evolutionary stage. That stage was the late phase of core carbon burning. The math gave them a star with a mass of about 11 to 12 solar masses today, which would have started life with roughly 9 solar masses at birth. The luminosity and surface temperature matched Betelgeuse's measured values. The synthetic light curve generated by combining the fundamental and first overtone modes looks similar to the actual observed brightness pattern of Betelgeuse up to the Great Dimming. Everything fit. If carbon burning lasts about 1,000 years for a star this size, and Betelgeuse is in the late phase of that stage, then the time remaining is far shorter than astronomers had previously assumed. After carbon burning ends, the star would move quickly through neon burning, then oxygen burning, then silicon burning, then collapse. Those final stages combined take less than a decade. So if Betelgeuse is genuinely close to the end of carbon burning, the supernova really could be within the lifetimes of people alive today. The paper made waves. News outlets around the world ran headlines suggesting that Betelgeuse could explode at any moment. Public excitement spiked. The combination of a famous star, a dramatic prediction, and a credible scientific source produced exactly the kind of viral moment astronomy rarely experiences. But the Sayo team was careful in their actual paper. They did not claim that Betelgeuse would explode within tens of years. They claimed that the star was in a late stage of core carbon burning, which is a statement about the current evolutionary stage, not a precise countdown. The tens of years figure was a possibility, not a prediction. The paper acknowledged that the exact evolutionary stage could not be pinned down with certainty. That nuance got lost in much of the popular coverage. The headline was the dramatic timeline. The fine print was the uncertainty, and the fine print mattered enormously for understanding what the paper actually said. The Sayo result is real and respected. It just isn't the only result. Other teams reading the same data have come to very different conclusions, and the disagreement is at the heart of why predicting Betelgeuse's death is so hard. For every team arguing that Betelgeuse is on the verge of exploding, there's another team arguing the opposite. The competing view, based on different assumptions and different observations, suggests that the star has many thousands of years left before the supernova. Both sides are reading legitimate science. Both sides have credible models. They just disagree about which evidence matters most. One of the influential alternative results came from a team led by Kenichi Nomoto and his colleagues at the Kavli Institute in Tokyo. Their analysis, published several years before the Sayo paper, came to a strikingly different conclusion. They argued that Betelgeuse was actually in the early core helium-burning phase of its life, not the late carbon-burning phase. If that's correct, the star has more than 100,000 years before it explodes. The timescale is so different from the tens of years prediction that it might as well be a different star. How can two careful studies of the same object reach such opposite conclusions? The answer lies in which features of Betelgeuse you treat as fundamental and which you treat as secondary. The Nomoto team focused on the star's overall properties, its size, its luminosity, its surface temperature, and matched those to evolutionary models. Their results pointed to a younger, smaller, less evolved star than the carbon-burning interpretation would predict. They also concluded that Betelgeuse is closer to Earth than some other estimates, perhaps closer to 500 light-years rather than 650, which changes the implied size and brightness calculations. Other researchers have pointed out that even the carbon-burning interpretation, if correct, doesn't necessarily mean the explosion is close. The carbon-burning phase for a star this size lasts roughly 1,000 years. Saying Betelgeuse is in the late stage of that phase still leaves significant room. Late could mean the last few decades, or it could mean the last few hundred years. The data is not precise enough to distinguish those scenarios with certainty. There's also a deeper problem. When a massive star approaches the end of its life, the surface conditions barely change during the final stages. Most of the action is hidden inside the core, sealed off from view by hundreds of thousands of miles of gas that the explosion energy hasn't reached yet. Even astronomers using the best telescopes available can only see the outer layers of Betelgeuse. The core itself is invisible. We can infer what's happening down there from pulsation behavior and surface chemistry, but the inferences carry significant uncertainty. The SCIO paper itself acknowledged this limitation. The authors noted that surface conditions hardly change in the late stage close to carbon exhaustion and beyond. Once a star reaches that phase, observational evidence becomes ambiguous. Carbon burning could continue for a long time without producing obvious external signs, or it could end abruptly. The same surface looks similar in either case. The result is a wide range of credible predictions. Some teams say tens of years, other teams say thousands. Most working astronomers, when pressed, will admit the honest answer is somewhere in between, with massive uncertainty bars. Betelgeuse will explode. That much is certain. When it explodes is genuinely unknown. Recent analyses have pulled the predictions in different directions again. The discovery of Sawaha in 2025 reshuffled some of the calculations, since adding a companion star to the model changes how Betelgeuse's behavior should be interpreted. Some of the strange pulsation features that were previously taken as evidence of late carbon burning might actually be artifacts of the binary interaction, in which case the case for an imminent explosion weakens. The honest summary is unsatisfying. We don't know. The argument over Betelgeuse's lifespan is not going away. It's not the kind of disagreement that one new paper or one good observation will resolve. The reasons for the persistent uncertainty are baked into the physics of massive stars themselves, and understanding why no one can settle the question reveals something important about the limits of stellar science. The first problem is that we have only one Betelgeuse to study. Stars like this are rare. Red supergiants nearing the end of their lives are scattered thinly across the galaxy, and most of them are far enough away that we cannot resolve their surfaces or measure their pulsations with the precision we get from Betelgeuse. The star is essentially a sample size of 1, which makes statistical claims about its evolutionary stage extremely difficult. We cannot compare its current behavior to a population of similar stars and confidently place it on a timeline. The second problem is that stellar evolution models are sensitive to assumptions. When you build a computer simulation of how a massive star ages, you have to make choices about how to handle convection, mass loss, rotation, magnetic fields, and many other physical processes. Different choices produce different predictions. A reasonable change in one parameter can shift the predicted lifetime by tens of thousands of years. Different research groups make different choices, and their predictions differ accordingly. The spread in published estimates for Betelgeuse's remaining life reflects this modelling sensitivity, not just measurement error. The third problem is the asymmetry of the final stages. As we mentioned, the surface of a massive star doesn't change dramatically once carbon burning is well underway. The star burns through neon, oxygen and silicon in increasingly short bursts, but each transition happens deep in the core, with limited visible consequences for the outer layers. By the time we'd see clear surface signs of imminent collapse, the supernova would already be hours away. There's almost no warning window from the outside. This is not unique to Betelgeuse. It's a general feature of how massive stars die. The end approaches in a way that's deliberately hard to detect from far away. Nature has not arranged for convenient countdown timers visible from Earth. The fourth problem is the binary system complication. Adding Sawaha to the picture changes how we should interpret almost everything we see. The pulsation patterns might be partially driven by binary interaction. The brightness variations might include effects from Sawaha's wake. The mass loss rate might be affected by the companion's gravitational stirring. Every observation is now contaminated by uncertainty about how much of what we see is intrinsic to Betelgeuse and how much is caused by the companion. The fifth problem is observational bias. We've had detailed observations of Betelgeuse for only about a century, which is a tiny slice of its life. The pulsation cycles we've measured might or might not be representative of the long-term behaviour. The Great Dimming might have been a one-time event, or might be a recurring feature on a longer timescale than our observation window. Without longer baselines, we cannot tell which short-term patterns are typical. Together, these problems mean that any prediction about Betelgeuse's lifetime carries enormous uncertainty. Astronomers who say tens of years and astronomers who say thousands of years are both being honest about what their analyses suggest. The disagreement is not about who is making mistakes, it is about which assumptions to trust when the data are ambiguous. And the data may stay ambiguous until the moment the explosion finally happens. That is a frustrating situation for everyone involved. It is also the actual state of the science. Strip away the surface layers of Betelgeuse and you'd find a structure that looks like the layers of an onion, except every layer is on fire. Each shell is burning a different element. The outermost shell, where the star meets space, is mostly hydrogen and helium, the fuels of stars early in their lives. Below that, deeper toward the centre, the layers grow hotter and denser, and the elements being fused get heavier and heavier. Hydrogen burning ended for Betelgeuse millions of years ago. The hydrogen fusing core collapsed under its own weight, heated up, and began fusing helium into carbon and oxygen. That stage lasted hundreds of thousands of years. When the helium ran out, the core collapsed again, heated up further, and began fusing carbon into neon, sodium, and magnesium. That's the stage Betelgeuse is in right now, somewhere along the carbon burning phase that lasts about 1,000 years for a star this size. Each new fuel is harder to burn than the last. Hydrogen fuses at about 10 million degrees, helium needs 100 million degrees, carbon ignites at 600 million degrees. Neon, oxygen, and silicon require even more extreme temperatures. As the star moves up the periodic table, the central temperatures climb into ranges that make a stellar core look more like the inside of a nuclear weapon than anything we usually associate with the word star. Each new fuel also burns much faster. The fuel burned in each stage produces less energy than the one before, but the energy is still being radiated away at the star's enormous luminosity. To keep up with that radiation loss, the core has to burn through fuel at increasing rates. Hydrogen lasted millions of years. Helium lasted hundreds of thousands. Carbon lasts about 1,000. Neon will last around 1 year. Oxygen will last a few months. Silicon will last about a single day. That accelerating timeline is one of the strangest features of dying massive stars. The final stages compress entire phases of nuclear physics into vanishingly short windows. By the time silicon burning starts, the star is essentially on a 1-day countdown, and there's no way to slow it down. the core is committed to the sequence by basic physics. While the core burns through its fuel, the outer layers are along for the ride. Most of Betelgeuse's volume is outside the active burning regions, just a vast envelope of cooler gas held up by radiation pressure from below. The outer layers don't know what stage the core is in. They respond to the energy flowing out of the core, but they don't have detailed information about which element is currently fusing. From outside, the only signs of the deep stages are subtle. This is part of why predicting the supernova is so hard. The outer layers, which is all we can see, look basically the same during late carbon burning as they will during oxygen burning a few hundred years later. The surface temperature, the brightness, the pulsation periods, all these features change slowly and ambiguously in the final stages. The dramatic action is happening invisibly, deep inside, beyond our reach. When silicon burning ends, the core fills up with iron. Iron is the element where stellar fusion stops being profitable. Fusing iron does not release energy. It absorbs energy. So when the iron core grows large enough, it suddenly cannot support its own weight against gravity. The whole structure collapses inward at a quarter of the speed of light. In less than a second, the core compresses into a neutron star or a black hole, and the rebound from that collapse blasts the outer layers of the star outward in a supernova. That's the moment everyone is waiting for, and the warning, when it finally comes, will arrive in a strange and unexpected form. When a massive star collapses, the first messengers to leave are not photons of light. They're particles called neutrinos, and they reach Earth before the explosion becomes visible. Understanding why is one of the strangest details of supernova physics, and it's the reason astronomers have built elaborate warning systems buried deep underground. Neutrinos are tiny, almost massless particles that barely interact with matter. They pass through ordinary objects like the objects aren't there. Right now, trillions of neutrinos from the sun are streaming through your body every second. You don't feel them, you can't see them. Most of them sail completely through Earth and out the other side without hitting a single atom. When a star like Betelgeuse collapses, the core is compressed into nuclear densities so extreme that the protons and electrons inside fuse together into neutrons. That fusion releases an enormous burst of neutrinos, more than 99% of the total energy of the supernova. The numbers are staggering. A core collapse supernova releases more energy in neutrinos in a few seconds than the Sun will produce in its entire 10 billion year lifetime. It's the most powerful neutrino source in the universe. The neutrinos escape immediately. Because they barely interact with matter, they fly straight out of the collapsing core and into space at nearly the speed of light. The visible explosion, the photons we associate with a supernova, doesn't escape immediately. The light has to fight its way out through the dense outer layers of the star, which can take hours. So the neutrinos arrive first. For Betelgeuse, the timing matters. Neutrinos from the supernova would reach Earth roughly 650 years after the collapse, the same as the visible light. But within the supernova event itself, the neutrinos lead the photons by a few hours. If we can detect the neutrino burst, we get an early warning that the visible explosion is about to start. This is not theoretical. We've done it before. In 1987, a supernova exploded in the Large Magellanic Cloud, a small galaxy near our own. Neutrino detectors in Japan, the United States, and the Soviet Union all caught a burst of neutrinos a few hours before astronomers spotted the visible explosion. The detection was historic, the first confirmation that supernovae really do release the predicted neutrino flood. It also proved that the early warning concept worked. For Betelgeuse, the warning would be much louder. The star is about 100 times closer to us than the 1987 supernova. The neutrino flux at Earth would be 10,000 times stronger. Every neutrino detector on the planet would light up like a Christmas tree, registering thousands of interactions in a few seconds. There would be no doubt about what happened. The signal would be unmistakable, and it would arrive hours before any optical telescope could see the explosion. That window is precious. A few hours of advance notice gives astronomers time to prepare. Telescopes around the world could be redirected to point at Betelgeuse. Observatories that had been doing other work could drop everything and aim at Orion. Even amateur astronomers with backyard telescopes could get their cameras ready. The first moments of the visible explosion are scientifically priceless, and any preparation time we can get is worth its weight in gold. The warning system already exists. Several international networks of neutrino observatories are connected through what's called the Supernova Early Warning System, which automatically distributes alerts when multiple detectors pick up a coordinated burst. If Betelgeuse goes, the alert will be flying around the world within minutes. Deep beneath a mountain in central Japan, a tank the size of a 14-story building sits in the dark, watching for the death of stars. The instrument is called Super Kamiokande, and it has been running for nearly 30 years. Its job is to catch neutrinos as they pass through Earth, and it's one of the primary listening posts for the Supernova Early Warning Network. The tank holds 50,000 tons of ultra-pure water. Ordinary water from your kitchen tap would be useless for this kind of work. The water inside Super Kamiokande has been filtered, distilled, and purified to almost unimaginable cleanliness, removing radioactive contaminants that would otherwise drown out the faint signals scientists are looking for. The walls of the tank are lined with thousands of light detectors, each one watching every cubic inch of the water for the briefest possible flash. When a neutrino interacts with an atom in the water, it produces a charged particle moving faster than light moves through that water. Light slows down when it travels through water. Charged particles can move faster than this slowed down light, and when they do, they emit a faint blue glow called Cherenkov radiation. It's similar in principle to the sonic boom of a supersonic jet, except with light instead of sound. The light detectors on the tank walls catch these blue flashes and record exactly when and where they appeared. By analysing the timing and pattern of the flashes, physicists can reconstruct what kind of neutrino interacted, where it came from, and how energetic it was. Most of the time, the detector picks up neutrinos from the sun, from the atmosphere, from cosmic rays. The background rate is steady and predictable. A supernova would produce a sudden, massive burst that would dwarf everything else by orders of magnitude. Super Kamiokande is not alone. Similar detectors exist around the world. There's one in Antarctica called IceCube, which uses a cubic kilometre of ice as its detection medium, with strings of light sensors lowered into the deep ice. There's one in Italy called Borexino, which used a different liquid medium until its recent retirement. There are detectors in China, Canada, the United States, and elsewhere. Each one operates independently, but they're all networked through the Supernova Early Warning System. The reason for the network is that no single detector can be trusted alone. False alarms happen. Cosmic rays, electronic noise, even occasional small earthquakes can produce signals that look briefly like a neutrino burst. To confirm a real supernova, multiple detectors at different locations have to see the same burst at the same time, with the right pattern. If 3 or 4 detectors all light up simultaneously with a coordinated signal, the alert is real. When that happens, an automated system sends notifications to telescopes and observatories around the world. The message is simple. A supernova has been detected. Drop what you're doing and observe. The timing and rough direction are included, so astronomers can immediately point their instruments at the right patch of sky. For Betelgeuse, the signal would be impossible to miss. Super Kamiokande alone might detect tens of thousands of neutrinos in a few seconds. IceCube would see a similar flood in its ice. The combined data would not just confirm the supernova, it would let scientists study the collapse in unprecedented detail. We would learn exactly how the neutrinos arrive, in what order, with what energies, and how the burst evolves over its few seconds of duration. That information would test theories of nuclear physics that have never been verified at supernova energies. The system is ready, the detectors are running. If Betelgeuse goes tonight, the alarm will sound within minutes. After the neutrino warning arrives, the world holds its breath. The visible explosion is on its way, but it takes time to emerge. The collapse happens at the centre of Betelgeuse. The light from that collapse has to fight outward through hundreds of thousands of miles of stellar gas before it reaches the surface and escapes into space. That journey takes hours, sometimes longer. During those hours, telescopes around the world are scrambling. The neutrino alert specifies the source direction with reasonable precision, and Betelgeuse is so prominent that there's no ambiguity about which star is exploding. Every instrument capable of looking at Orion gets pointed at the same patch of sky. Space telescopes get reoriented, ground-based observatories postpone whatever they were working on. Amateur astronomers around the world get text messages from coordinating networks. The build-up is electric. When the visible light finally breaks through, it appears as a sudden, dramatic brightening of Betelgeuse. The first phase is called shock breakout. The shock wave from the collapsing core finally reaches the surface of the star, and a burst of intense radiation is released in a single flash. The flash is short, lasting maybe an hour or two, and it's mostly in ultraviolet and X-ray wavelengths. Space-based observatories with the right instruments would catch this phase clearly. From the ground, the visible light brightening starts more gradually. Within the first day, Betelgeuse becomes much brighter than any normal star in the sky. Within a week, it outshines Venus. Within a month, it might rival the full moon at peak brightness. The star, which had glowed at first magnitude for centuries, suddenly becomes a beacon visible during the day. People who never look at stars would notice. The familiar shape of Orion would be altered beyond recognition, with the right shoulder transformed into a blazing point of light that dominates everything around it. The colour would shift over the first weeks. Early on, the explosion would appear bluish-white as the hottest layers of the expanding debris emit most of the light. As the debris expands and cools, the colour would shift toward yellow, then orange, then red, eventually fading toward dim crimson over the following months. The whole light show would be visible to the naked eye for several months, then continue at fainter levels for several years. The peak brightness would be extraordinary. Estimates suggest Betelgeuse could reach an apparent brightness comparable to the half moon, possibly brighter. It would cast clear shadows on the ground at night. Reading by Betelgeuse light might become a real possibility for a few weeks after the peak. People who happen to be outdoors during peak brightness would experience a kind of light no one has experienced in human history, a single point source so intense that it warps your sense of what a star can do. During daytime, the supernova would be visible against the blue sky. You wouldn't need binoculars or special equipment, just look up. There it would be, a bright star hanging in the daylight sky for weeks, slowly fading from view as the months wore on. Historical records of past supernovae mention exactly this kind of daytime visibility. The supernova of 1054 AD, which produced what we now call the Crab Nebula, was visible during the day for almost a month, according to Chinese astronomers who recorded it. The first hours of the light arrival from Betelgeuse would be the most photographed event in astronomical history. Every space telescope, every ground-based observatory, every advanced amateur setup, every smartphone with a clear view of Orion would be capturing data. The total volume of observations would dwarf anything ever collected before. The brightness of a Betelgeuse supernova is hard to grasp without comparisons. Astronomers measure stellar brightness using a scale called magnitude. Lower numbers mean brighter objects. The full moon shines at about magnitude -13. The brightest stars in the night sky sit around magnitude 1. Venus, when it's at its brightest, reaches about -4.7. A Betelgeuse supernova, based on the star's distance and the energy output of typical Type II supernovae, would peak at around magnitude -10 to -12. That puts it firmly between Venus and the full moon. Some calculations suggest the peak could be even brighter, possibly approaching the moon in raw output. The numbers vary depending on which model you use and how the explosion's geometry plays out, but the basic picture is consistent. We're talking about a single point of light bright enough to be the most prominent object in the sky after the moon and the sun. For a few weeks at peak, the supernova would be visible to anyone with eyes. You wouldn't need to know where to look. You'd just glance up and there it would be, an intensely bright star at the right shoulder of Orion, brighter than anything else in the sky except the moon. The familiar constellation would still be recognizable, but the proportion would be wrong. Orion's shoulder would be wildly out of scale, dominating the figure. The visual effect on the night sky would last for many months. Even after Betelgeuse passed peak brightness, it would remain naked eye visible for years. Eventually it would fade below the magnitude limit for human vision, but during the long fade, it would still rank as one of the brightest stars in Orion. The constellation as we know it would never look quite the same again, even decades after the explosion. For amateur astronomers and casual stargazers, the experience would be a generational event. Most people have never seen a naked-eye supernova in their lifetime. Most won't see one in their entire life unless they're lucky. The last one visible from Earth without a telescope, called Kepler's supernova, was observed in 1604. Before that, the so-called Tycho's supernova in 1572. Both were spectacular events that influenced the course of astronomy for centuries afterward. Betelgeuse would join that very short list, and it would be by far the closest and brightest of them. There's a subtle point about the brightness that's worth mentioning. The numbers describe what we'd see from Earth, accounting for the distance Betelgeuse light has to travel. The actual energy output of the explosion would be vastly greater. If you were close to the supernova, say within a few light years, the brightness would be lethal. The radiation alone would scorch any nearby planet. Anything within tens of light years would be in serious danger. We are safe at 650 light years away, but the explosion is genuinely a galactic scale event, not just a pretty light in the sky. For the months it shines at peak, Betelgeuse would change everyday life in subtle ways. People accustomed to looking at the night sky would notice immediately. People who never thought about astronomy would still hear about it from news reports, social media, and conversations with friends. The supernova would be a topic of public interest for weeks, then months. Schools would teach lessons about what was happening, planetariums would run special programs, religious and spiritual interpretations would emerge from various traditions, as they have for every previous bright supernova in human history. This is the kind of event that gets written into the history books. People living through it would remember exactly where they were when they first saw it, and the light from the explosion would keep arriving for years. The Betelgeuse supernova will be a beautiful event, but it will also create some practical problems for human technology. Modern civilization depends heavily on satellites, communication networks, and electronic systems that are vulnerable to certain kinds of radiation. A nearby supernova produces a flood of high-energy particles and gamma rays that can affect these systems. Most of the danger is far less than science fiction dramas suggest, but some real concerns exist. The first issue is the gamma ray and X-ray pulse from the early phase of the explosion. When the shockwave breaks through the star's surface, a burst of high-energy radiation is released. This burst travels at the speed of light and arrives at Earth simultaneously with the visible flash. Gamma rays and X-rays don't make it through Earth's atmosphere to the ground, but they can affect satellites in orbit and the upper layers of the atmosphere itself. For satellites, the gamma ray pulse from a Betelgeuse supernova would be intense, but not catastrophic. Modern satellites are designed to handle solar flare events that produce comparable radiation levels. Some sensitive electronics might glitch. A few older or less protected satellites might suffer permanent damage. The overall fleet would survive, though some operational disruptions would occur during the peak of the radiation event. The bigger concern is the upper atmosphere. The X-ray and gamma-ray flux from a relatively close supernova can dissociate ozone molecules in the stratosphere, temporarily depleting the ozone layer that protects Earth from ultraviolet radiation. Studies of past supernovae and modelling work suggest that a Betelgeuse-distant supernova could reduce global ozone by a few % for a period of months to years afterward. The effect would not be catastrophic. Skin cancer rates might rise modestly, crop yields might be slightly affected, but humanity would not be at existential risk. Cosmic rays are the second wave of concern. Supernovae are major producers of high-energy particles, and the debris from the explosion gradually accelerates protons and atomic nuclei to nearly the speed of light. These cosmic rays don't arrive immediately. They take thousands or hundreds of thousands of years to reach us, because they bend in the magnetic fields of interstellar space and follow long, twisted paths. Earth would experience a slow, sustained increase in cosmic ray flux over a long period after the explosion. The increase would be measurable, but small compared to the natural background. Another worry sometimes raised in popular discussions is whether a supernova could trigger mass extinctions on Earth. The science suggests this requires a much closer event than Betelgeuse. Studies of the geological record have looked for signatures of past supernovae and have found evidence for nearby explosions in deep time, including a possible event around 2.5 million years ago that may have left traces in ancient ocean sediments. Those events occurred at distances of tens of light years. Betelgeuse at 650 light years is far enough away to spare us from that level of damage. There's one more practical issue. The visible brightness of the supernova would be intense enough to interfere with astronomical observations of fainter objects in the same part of the sky. For months, anything near Orion in the celestial sphere would be hard to study because the supernova's glare would overwhelm sensitive detectors. Telescopes would need to work around the bright source, scheduling observations to avoid having Betelgeuse in the field of view. This is a relatively minor inconvenience, but it would affect research programs that happen to involve targets near Orion. Overall, the threat assessment for a Betelgeuse supernova lands in the same place. The event would be spectacular, technologically annoying for a while, and biologically harmless to humans. The danger is real, but limited. We are far enough away to enjoy the show without paying a serious price. The reason Betelgeuse poses no serious danger to Earth comes down to a simple physical principle. Radiation intensity drops with the square of the distance from the source. If you double your distance from a light, you receive a quarter of the brightness. Triple the distance, and you receive a ninth. The drop-off is rapid, and over the vast distances of interstellar space, even powerful events become tame by the time their effects reach us. Betelgeuse is 650 light-years away. That's about 4 trillion miles. The number is so big that human intuition fails. To put it in perspective, light from the Sun reaches us in 8 minutes. Light from the next nearest star, Proxima Centauri, takes a little over 4 years. Light from Betelgeuse takes more than 6.5 centuries. The star is far enough that the supernova's effects, which would be devastating up close, are diluted to manageable levels by the time they cross the gap to us. Astronomers have a rough rule of thumb for supernova safety distances. The conventional estimate is that a Type II supernova would need to be within about 50 light-years of Earth to cause severe biological damage. Even at that distance, the threat would come mainly from sustained cosmic ray flux and atmospheric chemistry changes rather than from the initial radiation burst. At 100 light-years, the effects would be measurable but probably not catastrophic. At several hundred light-years, the damage drops to barely detectable levels in ecosystems. Betelgeuse at 650 light-years sits firmly in the safe zone. The supernova would shine brilliantly in the sky, dump some extra cosmic rays into the solar system over the following millennia, and slightly affect our atmosphere for a few years. It would not threaten human survival. It would not cause mass extinctions. It would not permanently damage the biosphere. The light show would be the main event, and the light show is harmless. This is fortunate from a sensible distance standpoint, but it's also worth recognizing how lucky we are in a broader sense. There are massive stars closer to Earth than Betelgeuse, but most of them are not on the verge of exploding. There are also ancient supernova remnants in our galactic neighborhood, leftover bubbles of gas from explosions that happened thousands or millions of years ago at relatively close distances. We've survived all of them. The distribution of nearby massive stars and the timing of their explosions has worked out in our favor over the long run. There's an interesting historical wrinkle here. Some scientists have suggested that ancient supernovae much closer than Betelgeuse may have left their fingerprints in Earth's geological record. Iron isotope evidence in ocean sediments suggests that one or more supernovae exploded within about 100 light-years of Earth a few million years ago, possibly within 50 light-years. These events would have produced measurable but not catastrophic effects on the climate and biosphere. Some researchers have speculated that they might be linked to certain extinction events or evolutionary transitions, but the evidence is debated. Whatever happened in the deep past, Betelgeuse today is too far away to repeat that kind of close encounter. The geometry is just not threatening. The light when it arrives will be beautiful and bright, but it won't be dangerous to anyone who isn't trying to stare directly at it through a powerful telescope. For perspective, even the brightest possible Betelgeuse supernova would deliver less ultraviolet radiation to Earth than a single hour of normal sunlight. The brightness on a clear day is dominated by our local star, 8 light-minutes away, which is overwhelmingly closer than anything else in the sky. The supernova would compete with stars and the moon, not with the sun. We are safe to enjoy it without worry. Here's a strange thought experiment. Imagine that Betelgeuse exploded last week. The supernova flash, the brightest event in the local universe for millions of years, has already occurred. A wave of light is currently expanding outward from the site of the explosion, sweeping through interstellar space at the speed of light. Right now, somewhere out there, that wavefront is closing in on Earth, but we don't know about it yet. We can't know. The light hasn't arrived. From our perspective, the star still glows in Orion, looking the way it has looked for centuries. The information about the explosion has not had time to travel the 650 light-years between Betelgeuse and us. From our vantage point, the supernova has not happened yet, even if in some absolute cosmic sense, it already did. This is a real consequence of the finite speed of light. When we look at any distant object, we're seeing it as it was when the light left it, not as it is right now. Betelgeuse appears to us today as it was around the year 1375. Anything that happens to the star now, we won't see until around 2675. There's a 6.5-century delay built into every observation we make of it. For supernovae, this delay creates a particular philosophical puzzle. The event might already be over, and we have no way to know. The neutrinos arrive at the same time as the light, so even our advanced warning systems can't peek behind the delay. We're stuck waiting for information that's been travelling for centuries to finally reach us. There's no way to estimate the probability that Betelgeuse has already exploded. The calculation depends on knowing exactly when the star will explode in its own time frame, which is precisely the question we cannot answer. If Betelgeuse exploded 600 years ago, the light would arrive in about 50 years. If it exploded 1,000 years ago, the light arrived 350 years ago, which means we should already have seen it, which means it didn't happen. If it exploded yesterday, we have 650 more years to wait. What we can say is that every passing day brings us closer to whatever the answer turns out to be. If Betelgeuse exploded yesterday, the light is now 1 day closer than it was the day before. If the explosion is still in the star's future, the time until it happens is 1 day shorter than yesterday. Either way, the wait is decreasing. The only thing we don't know is which kind of waiting we're doing. This is one of the genuinely unique features of Betelgeuse as a research target. With most distant astronomical objects, the time delay between them and us is so vast that the question doesn't feel personal. The light from a galaxy 1 billion light-years away left when life on Earth was just multicellular, and whatever happens to that galaxy now is almost meaningless in human terms. Betelgeuse is different. 6.5 centuries is a manageable timescale. The light that's leaving the star right now will be visible to people not so far in the future, and the people who eventually see whatever happens will be our descendants in a fairly direct sense. There's something beautiful about this. The supernova, when it eventually appears in our skies, will be a message from a star that has been dead for centuries. We will be witnessing an event that ended a long time ago, played out in light that has been travelling toward us patiently across the stars. The time delay turns the supernova into a kind of cosmic letter, mailed long ago and finally arriving. Whether the letter is already in the mail or still being written, we cannot say. We will find out when we find out. The future of Siwaha is grim. Orbital mechanics and stellar physics have already determined the small star's fate. It will not survive its long partnership with Betelgeuse. The only question is which of two endings reaches it first. The first possibility is the merger. As Siwaha ploughs through Betelgeuse's outer atmosphere on every orbit, friction with the gas slowly drains energy from the orbit. The companion is gradually spiralling inward. The rate of inward spiral is slow on human timescales, but inevitable on stellar ones. Given enough time, Siwaha will dive deeper into Betelgeuse's atmosphere with each pass, until eventually a single orbit takes the small star into regions dense enough to disrupt it completely. At that point, Siwaha plunges into the giant. What happens next is dramatic. A merger between a normal star and a red supergiant is a violent event. The companion, falling toward the giant's core, releases enormous amounts of gravitational energy as it descends. That energy heats the surrounding gas, causes ejections of material from the outer layers of Betelgeuse, and potentially produces a temporary brightening that could be visible from Earth. From outside, the merger event might look like a dramatic flare or even a small explosion, although it would be very different from the eventual supernova. The merger would also fundamentally reshape Betelgeuse. Adding the mass of Siwaha to the giant changes the total mass of the star. Adding the angular momentum of Siwaha's orbital motion changes how fast Betelgeuse rotates. Spinning a red supergiant up could affect everything from its magnetic activity to its mass loss rate to the eventual character of its supernova explosion. A spun-up Betelgeuse might explode asymmetrically, producing a lopsided debris cloud and a kicked-out neutron star moving at high speed through the surrounding space. The second possibility is that the supernova happens first. If Betelgeuse runs out of fuel before Siwaha completes its inward spiral, the explosion arrives while the companion is still in its orbit. In that case, Siwaha would be caught in the blast wave. A small star sitting just a few astronomical units from a core collapse supernova has no chance of surviving. The radiation flux alone would vaporize it. The blast wave would tear what remained into atomic debris that mixed with the rest of the supernova ejecta. In some sense, this second ending is cleaner. There's no slow spiral, no extended stress on the orbital mechanics, just a sudden destruction in a moment of cosmic violence. The companion that has been orbiting Betelgeuse for who knows how long would simply cease to exist when the giant tore itself apart. The current best guess from astronomers is that the merger probably happens before the supernova, although the timing is uncertain. The orbital decay rate suggests that Siwaha could fall into Betelgeuse within perhaps tens of thousands of years, possibly much sooner. If the supernova is also that close, the race between merger and explosion is genuinely close. We may end up watching one or both events from Earth. Either ending would be scientifically priceless. A pre-supernova merger between a giant and its companion has never been observed in detail. We've seen a few cases that might have been mergers, including some unusual brightening events in distant galaxies, but the data is limited. Watching Siwaha fall into Betelgeuse from our front row seat would teach us things about binary star evolution that we cannot learn any other way. Watching the supernova catch Siwaha mid-orbit would let us see how an explosion interacts with a companion star in real time. Either outcome ends the same way for Siwaha. The companion's days are numbered. The countdown is already running. If Siwaha does merge with Betelgeuse before the supernova, the consequences for the eventual explosion would be significant. Astronomers believe that mergers between giant stars and their companions are responsible for some of the strangest features observed in supernova remnants throughout the galaxy. A pre-explosion merger leaves fingerprints on the explosion itself, and those fingerprints can last for thousands of years afterward. The first effect is on the geometry. A red supergiant that has just absorbed a companion star is unlikely to be perfectly symmetric. The merger event would have churned up the outer layers, redistributed mass unevenly, and possibly created a thick disk of leftover material around the giant's equator. When the supernova later explodes, the blast wave would not expand uniformly in all directions. It would push more easily through some regions and meet resistance in others, producing a lopsided debris cloud, we can see evidence of this kind of asymmetry in older supernova remnants throughout the galaxy. Some remnants show clearly elongated shapes, with material extending much farther in one direction than another. Some show ring-like structures that look like the leftovers of pre-explosion disks. Some show evidence that the central neutron star was kicked off in a particular direction, which can happen if the explosion was asymmetric and the recoil pushed the neutron core away. A pre-merger event could create exactly these kinds of features. The second effect is on the spin. Merging Sawaha into Betelgeuse would deliver a large amount of angular momentum to the giant. Red supergiants typically rotate slowly. Betelgeuse, in particular, has been observed to rotate faster than expected, which some researchers have already attributed to a possible past merger with another companion that no longer exists. Adding Sawaha to the system would spin Betelgeuse up further. The supernova, when it eventually happens, would inherit that rotation. A fast-spinning core collapsing to form a neutron star tends to produce more violent and asymmetric explosions, with potential consequences for the resulting brightness, light curve shape, and remnant structure. The third effect is on the chemistry. Different stars have slightly different compositions depending on how they formed and what stage of life they're in. Mixing Sawaha's material into Betelgeuse's outer layers would create an unusual chemical signature in the eventual supernova ejecta. Astronomers studying the explosion's spectrum would be able to detect this mixing, providing direct evidence that a merger had taken place. The chemical fingerprint would persist in the supernova remnant for thousands of years, gradually fading as the gas dispersed, but visible in detailed spectroscopic studies. The fourth effect is on the timing. As we mentioned earlier, adding mass and angular momentum to a star near the end of its life can affect how quickly it reaches the supernova stage. Some models suggest the merger could shorten the time to explosion by destabilizing the core. Other models suggest the merger could provide a temporary stability boost, potentially delaying the supernova by some amount. The actual outcome depends on detailed parameters of both stars and the geometry of the merger, which we don't fully know yet. Watching all of these effects play out would be revolutionary for astronomy. Most of what we know about pre-supernova mergers comes from theoretical modelling and indirect inference. Direct observation of a merger followed by a supernova in the same star would let us test those theories with unprecedented precision. It would essentially be a controlled experiment, except the experiment is being conducted by nature on a scale we cannot replicate. The Sawaha discovery has transformed Betelgeuse from a single dying star into a complete laboratory for stellar evolution. The lessons we'll learn before, during, and after the explosion will reshape our understanding of how massive stars die. When Betelgeuse finally explodes and the supernova fades away over the following months and years, something will be permanently different about the night sky. The right shoulder of Orion will be gone. After centuries of glowing red and orange in the constellation's familiar pattern, the star will leave behind a hot, fading remnant that will not look anything like the original. Orion, as humans have known it for thousands of years, will be altered. The constellation has appeared in human cultural records for at least 5,000 years. Egyptian, Babylonian, Greek, Chinese, Indigenous American, and Aboriginal Australian traditions all recognise the same basic figure in the same patch of sky. Most of those traditions specifically note the bright star at the upper left, the one that appears redder than the others. Whether interpreted as a wound, a coal, a fire, or a hunter's eye, Betelgeuse has been part of the constellation's identity for as long as humans have looked up. After the supernova, that part of the constellation will be a hole. For a few months it will be a brilliant, almost blinding new star, but afterward it will fade quickly. Within a year or two, the fading remnant will dim below the brightness of nearby stars. Within a few years, it will dim below naked eye visibility entirely. The right shoulder of Orion will simply be empty space, without any visible star to mark the position. What replaces Betelgeuse will be a slowly expanding cloud of hot gas and dust, the leftover debris of the explosion, called a supernova remnant. For the first centuries afterward, the remnant will be visible only through telescopes, glowing faintly at various wavelengths as the hot gas cools and interacts with the surrounding interstellar medium. Eventually, over thousands of years, the remnant will expand into a beautiful ring or shell structure similar to the famous Crab Nebula or the Veil Nebula, both of which are remnants of past supernovae. At the centre of the remnant, a neutron star will likely remain. When the core of Betelgeuse collapses, most of the mass that doesn't get blown away in the supernova compresses into an object the size of a city, with the mass of more than the Sun packed into a sphere just a few miles across. This neutron star would have an extreme magnetic field, possibly rotate rapidly, and might be detectable as a pulsar emitting beams of radio waves and X-rays. Future astronomers studying the Betelgeuse remnant would be able to track the neutron star directly, adding it to the catalogue of known compact objects in our galactic neighbourhood. For a fraction of stars more massive than Betelgeuse, the core collapse forms a black hole instead of a neutron star. The current best estimates of Betelgeuse's mass suggest it's just below the threshold for forming a black hole, meaning a neutron star is more likely. But the threshold is uncertain, and the addition of mass from a Sawara merger could push the eventual collapse closer to black hole territory. Whichever object forms, it will be a kind of cosmic gravestone marking the location where Betelgeuse used to be. For human cultures that have looked at Orion for thousands of years, the loss of Betelgeuse will be a strange experience. The constellation will still be recognisable. The belt will still be there, the bright stars below the belt will still mark the lower body of the figure, and ridddle will still glow blue at the lower right. But the upper left will be missing the most visually distinctive part. Stories and traditions tied to the red shoulder of the hunter will have to adjust to a sky where that shoulder no longer exists. The change will be permanent on human timescales. Future generations will grow up looking at an Orion that lacks Betelgeuse. The star that has been on the upper left of the constellation for as long as humans have been looking will not return. The sky will be different forever. When the supernova fades and the dust settles, the remaining structure at the centre of the Betelgeuse remnant will be one of the most extreme objects in the universe. A neutron star is so dense that a sugar cube-sized piece of its material would weigh as much as a mountain on Earth. The physics of these objects pushes against the limits of what we understand, and having a fresh one in our cosmic backyard would be a tremendous research opportunity. A neutron star forms when the core of a massive star collapses under its own gravity. The protons and electrons in the core get squeezed together so violently that they merge into neutrons, releasing the burst of neutrinos that we discussed earlier. What's left is essentially a giant atomic nucleus, a sphere of pure neutron matter held together by gravity instead of by the strong nuclear force. The result is an object with the mass of about 1.5 suns packed into a ball roughly 12 miles across. The density at the centre of a neutron star is extraordinary. A teaspoon of neutron star material has a mass of about 1 billion tons. The surface gravity is so strong that an object falling from a height of 1 foot would hit the ground at 1/4 of the speed of light. The escape velocity from the surface is more than half the speed of light. These are not numbers that human intuition can really handle. They're just the consequences of compressing too much matter into too little space. Newly formed neutron stars often spin extremely fast. As the original stellar core contracts, conservation of angular momentum forces the spin rate to increase, similar to how a figure skater spins faster when she pulls her arms in. A neutron star can rotate hundreds of times per second when it first forms, although the rate slows over time as the star radiates energy away. Many neutron stars have intense magnetic fields, trillions of times stronger than the magnetic field of Earth. The combination of fast rotation and strong magnetic fields can produce beams of radio waves, X-rays, and gamma rays that sweep across space like the beam of a lighthouse. When the beam happens to point at Earth, we detect the neutron star as a pulsar, a regularly pulsing source of radio emission. Many of the pulsars in the galaxy are known to be the leftover cores of past supernovae. Whether Betelgeuse's remnant produces a detectable pulsar depends on the geometry of the magnetic field and how the neutron star is oriented relative to Earth. If the rotation axis happens to point in the right direction, we'd see clear pulses from the remnant within decades of the supernova. If it doesn't, we might still detect the neutron star through its X-ray emission or other signatures, but the spectacular pulsing pattern would be invisible to us. The neutron star might also be moving. Supernovae often kick their resulting compact objects in random directions due to asymmetries in the explosion. Many known neutron stars are moving through the galaxy at hundreds of miles per second, which is enough to send them flying out of the supernova remnant after a few thousand years. The Betelgeuse remnant could similarly produce a high-velocity neutron star that gradually drifts away from the original explosion site. In the very long run, the neutron star will stabilize into a quiet, slowly rotating object that will exist for a very long time. Neutron stars don't really age in the way stars do. They cool slowly over billions of years, their pulsar emission fading as their spin rate decreases. The neutron star left behind by Betelgeuse will outlast the Sun. It will continue its existence in the space where Orion's right shoulder used to be, marking the location of the old giant for as long as the universe remains capable of supporting structure at all. That's a strange thought. The marker will outlast almost everything else. After the immediate fireworks of the supernova fade, the resulting remnant will become one of the most studied objects in the galaxy. Supernova remnants are the laboratories where astronomers learn how stars distribute heavy elements throughout the cosmos, how shock waves interact with interstellar gas, and how the death of one generation of stars seeds the birth of the next. The remnant of Betelgeuse will start as a hot, glowing cloud of debris expanding rapidly outward from the original location of the star. In the early years, the cloud will be dense enough and hot enough to emit visible light. We will be able to study its expansion rate, its chemical composition, and its three-dimensional structure using a wide range of observational techniques. The cloud will be relatively small at first, just a few light years across, and astronomers will be able to map it in detail. As the years pass, the cloud will expand and cool. The leading edge, called the forward shock, will sweep up surrounding interstellar gas as it travels outward. The sweeping up creates a thin, hot shell of compressed gas that emits X-rays, radio waves, and other forms of radiation that telescopes can pick up. Over decades and centuries, the shell will grow to dozens or hundreds of light years across, eventually merging with the general interstellar medium and dispersing into the galactic background. During the centuries of the remnant's evolution, scientists will have access to a unique resource. They will be watching in real time the early stages of how heavy elements get distributed through the galaxy. Supernovae are responsible for producing most of the heavy elements in the universe, including the iron in your blood, the calcium in your bones, the gold in jewelry, and the silver in coins. All of these elements were forged inside dying stars and scattered into space by supernova explosions. The Betelgeuse remnant will let us watch the scattering process up close, seeing exactly how the freshly produced elements mix with the pre-existing gas in the surrounding region. The chemical fingerprint of the explosion will tell us a lot about what was happening inside Betelgeuse during its final stages. Different shells of the dying star produced different elements, and the explosion preserved that layered structure in the expanding debris. By measuring the composition of different parts of the remnant, astronomers can essentially read the cross-section of the original star's core, learning what fuel had been burning where in the years before the supernova. If a Sawara merger occurred before the supernova, the remnant will carry the chemical fingerprint of that merger as well. The added material from the companion star would create a distinctive chemical signature in certain regions of the debris. Detecting and mapping that signature would directly confirm the merger scenario, providing a crucial test of theories about how binary star systems evolved toward the end of their lives. The remnant will also serve as a target for studies of cosmic ray production. Supernova remnants are believed to be the primary sources of high-energy cosmic rays in the galaxy. The rapidly expanding shockwave accelerates particles to nearly the speed of light, sending them streaming outward into space. By observing the remnant in radio waves and X-rays, astronomers can directly study the acceleration process, testing theoretical models that have been built up over decades. Future generations of astronomers will continue to study the Betelgeuse remnant for thousands of years. Each century of observation will reveal new details as the cloud evolves. Children alive when the supernova happens will live through the most spectacular period of the remnant's visibility. Their descendants will inherit a research program that will continue producing scientific results long after living memory of the original explosion has faded. The remnant will be both a tomb and a textbook. The supernova will end Betelgeuse, but the leftover structure will keep teaching us about how stars die for centuries to come. A naked-eye supernova in our galaxy is a rare event. They happen, on average, only once or twice per century, and many of those go unnoticed because they're hidden behind interstellar dust or located in parts of the sky that aren't well observed. Humans have actually seen and recorded only a handful of galactic supernovae throughout written history. Each one was a major event, and their stories give us a glimpse of what the Betelgeuse explosion might be like for the people who eventually witness it. The earliest reliably recorded supernova happened in 185 AD. Chinese astronomers documented a guest star that appeared in the constellation Centaurus and remained visible for about 8 months. The detailed observations made by these astronomers have allowed modern researchers to identify the location of the supernova remnant in the sky, confirming that the historical record matched a real event. Another well-documented supernova flared up in 1006 AD. This one was probably the brightest stellar event ever recorded by humans. Observers in Egypt, China, Japan, the Arab world, and Europe all noted a star so bright that it cast shadows at night and was visible during the day for weeks. Modern estimates suggest this supernova reached an apparent brightness comparable to a quarter moon. The remnant is located in the constellation Lupus, and modern telescopes can still see the expanding debris from the explosion. In 1054 AD, another supernova exploded in the constellation Taurus. Chinese, Japanese, and Arab astronomers all documented the event, noting that the new star was bright enough to be visible during the day for almost a month. The remnant of this supernova is the famous Crab Nebula, one of the most studied objects in modern astronomy. The Crab contains a fast-spinning pulsar at its centre, the leftover neutron core of the original star. Tycho Brahe, the Danish astronomer, observed a supernova in 1572. The event was visible for about 18 months and reached a peak brightness comparable to Venus. Tycho's careful observations played an important role in the early scientific revolution, because they showed that the heavens were not unchanging as the prevailing Aristotelian doctrine had insisted. New stars could appear and disappear, suggesting that the universe was dynamic in ways that classical philosophy had denied. Johannes Kepler observed another supernova in 1604. This one reached a brightness comparable to Jupiter and remained visible for about a year. Like Tycho's supernova, Kepler's event challenged old ideas about the unchanging nature of the celestial sphere. Together, these two events helped pave the way for the scientific revolution that produced modern astronomy. Since 1604, no supernova has exploded close enough in our galaxy to be visible to the naked eye from Earth. The 4-century gap is unusual. Statistically, we'd expect a galactic supernova every 50 to 100 years on average. The recent quiet period is just bad luck, and astronomers have been waiting for the next one. A supernova in a nearby galaxy did appear in 1987, called supernova 1987A, but it was in the Large Magellanic Cloud rather than our own galaxy. It was only barely visible to the naked eye, and only from the southern hemisphere. A Betelgeuse supernova would shatter the 4-century drought spectacularly. It would be brighter than every historical supernova combined. It would be visible from both hemispheres. It would last for months at peak brightness, then years at lower brightness. It would be photographed, filmed, and analysed in ways that no previous supernova has ever been studied. The cultural impact would be enormous, comparable to or exceeding the impact of past historical supernovae. People living through it would know they were witnessing something genuinely once in history. The astronomical community has been preparing for a Betelgeuse supernova for decades. Observatories around the world have plans in place for what to do when the alert arrives. The first hours and days of a nearby supernova are scientifically priceless, and missing them is not an option for any team that wants to contribute to the historical record. The plan begins with the supernova early warning system, the network of neutrino detectors we discussed earlier. When that system fires, automated alerts go out to telescopes around the world. Observatories with rapid response capability can be pointed at Betelgeuse within minutes. Robotic telescopes that operate without human intervention can react even faster, beginning their observations before any astronomer is awake to oversee the process. The James Webb Space Telescope would be a key asset during the early phase of the explosion. Webb's infrared sensitivity would let it study the rapidly evolving debris cloud at wavelengths that ground-based telescopes can't easily observe. The first hours of the explosion produce mostly hot, ionized material that emits strongly in the infrared, and Webb's instruments are precisely tuned for this kind of work. Webb's schedule would likely be cleared to focus on Betelgeuse for as long as needed. The Hubble Space Telescope would also play a role. While Hubble is older than Webb, it has different strengths, including ultraviolet sensitivity that Webb cannot match. The early shock breakout phase of the supernova produces strong ultraviolet emission, and Hubble could capture the spectral features that reveal the conditions inside the expanding debris. Ground-based observatories around the world would coordinate their observations to provide continuous coverage. As Earth rotates, different parts of the world have different views of the sky. Observatories in Chile, Hawaii, the Canary Islands, Australia, and other prime astronomical sites would be linked into a global watch program, ensuring that someone is always recording data from the supernova at every moment of every day. The Vera Rubin Observatory in Chile, designed specifically for surveys of changing astronomical phenomena, would track the supernova's brightness over time with unprecedented precision. The Rubin's wide field of view would also let it monitor the surrounding region for any unusual features in the debris cloud or interactions with nearby gas. Its data archive would become a permanent resource for future astronomers studying the event. Radio telescopes would join the observation campaign as the explosion evolves. The early supernova doesn't produce much radio emission, but as the shock wave expands and interacts with the surrounding material, radio waves become an important way to track the developing remnant. Networks like the Very Large Array in New Mexico and the Atacama Large Millimeter Array in Chile would devote significant time to monitoring the radio evolution. Amateur astronomers would also contribute. The supernova would be bright enough that even small telescopes could capture useful data. Networks of amateur observers, coordinated through international organizations, would feed observations into databases that professional astronomers could use. The combined efforts of professionals and amateurs would produce a more complete record than either group could create alone. There would be competition among research teams to publish the first detailed analyses. The early supernova would produce papers in peer-reviewed journals within days of the first observations. The volume of new science generated by the event would dwarf almost any other astronomical event in history. Careers would be made by scientists who happened to be in the right place at the right time, with the right tools and the right preparation. The race is not just for prestige. Different observations made at different times provide complementary information about the supernova. The early phases reveal the structure of the dying star. The middle phases show how the explosion energy interacts with the surrounding material. The late phases trace the long-term evolution of the remnant. To understand the full picture, every phase has to be observed, and observed well. Missing any of it would leave permanent gaps in our knowledge. The world is ready. We've been ready for a long time. Beyond the spectacle, a Betelgeuse supernova would settle scientific debates that have been running for generations. There are questions about how massive stars die that we've only been able to address indirectly by studying distant supernovae or theoretical models. A nearby explosion would let us address those questions directly. The neutrino burst alone would test theories of nuclear physics that have never been verified at supernova energies. The exact pattern of neutrino emission, including how the burst evolves over its few seconds, would tell us how the core collapses, how the proto-neutron star forms, and how energy gets transferred from the core to the outer layers. Different theoretical models make different predictions for these patterns, and a clean detection from Betelgeuse would let us pick the right model. The shock breakout phase would test our understanding of how the explosion energy escapes from the dying star. The exact timing of the brightness rise, the spectrum of the early light, and the way the brightness changes over the first minutes and hours all depend on detailed properties of Betelgeuse's outer layers. Observations during this phase would reveal what the star's atmosphere actually looked like in the moments before the explosion, providing a snapshot of the late evolution that we cannot get any other way. The light curve over the following months would test models of how the radioactive elements produced in the explosion power the brightness during the long fade. Most of the visible light from a supernova in the weeks and months after the peak comes from the radioactive decay of nickel and cobalt produced in the explosion. The rate of fading depends on how much radioactive material was produced and how it's distributed in the debris. Detailed observations would let us measure these properties directly. The chemical composition of the debris would tell us what was happening in Betelgeuse's core during its final days. Different layers of the dying star produced different elements, and the explosion preserved that layered structure in the expanding cloud. Spectroscopy of the debris over time would let us reconstruct the internal structure of Betelgeuse before the supernova, essentially performing an autopsy on the star using its own scattered remains. If a Sawaha merger preceded the explosion, the chemical signature of the companion would be detectable in the debris. This would directly confirm the merger scenario and let us study how stellar mergers affect supernovae, an area that's been heavily theoretical until now. Even if no merger occurred, the chemical fingerprint of the binary interaction would be visible in the surrounding gas, telling us how Sawaha's wake had been reshaping Betelgeuse's atmosphere over the centuries before the explosion. The neutron star or black hole left behind would let us study the aftermath of core collapse in detail. Within months or years of the supernova, the central object would become detectable, and we'd be able to measure its properties precisely: its mass, its rotation rate, its magnetic field, its position relative to the explosion site. All would tell us how the collapse proceeded and how the asymmetries of the explosion affected the final outcome. The remnant's expansion in the years and decades afterward would test models of how supernova shockwaves interact with the surrounding interstellar medium. The Betelgeuse explosion would inject a huge amount of energy into the local region of the galaxy, sweeping up gas, accelerating cosmic rays, and reshaping the magnetic fields. We'd be able to watch all of these processes happen in real time, comparing them to predictions and refining our theories as the data accumulated. The cumulative knowledge gained would be transformative. Stellar physics, nuclear physics, particle physics, and galactic dynamics would all be advanced by the observations. Textbooks would be rewritten. Long-standing puzzles would be resolved or sharpened. The science of dying stars would enter a new era, dated from the moment Betelgeuse's light first reached our telescopes. That's why people are watching so closely. The payoff for being prepared is enormous. Before the explosion arrives, Betelgeuse is likely to give us a few more strange behaviours. The star is not going to slip quietly into the supernova phase. Massive stars near the end of their lives tend to become increasingly unstable in the years and decades before they explode, with surface activity, mass loss, and brightness fluctuations all intensifying as the core changes accelerate. We've already seen some of these warning behaviours. The great dimming of 2019 and 2020 was probably one of them, a violent ejection of material that may be linked to the late-stage instabilities affecting the star's outer layers, the unusual pulsation patterns, the asymmetries in the surface, the chemical signatures of fresh material being thrown into the outer atmosphere. All of these features fit the picture of a star approaching its final crisis. In the time before the supernova, expect more events like the Great Dimming. The star will continue to brighten and dim in unexpected ways. Mass ejections will happen periodically, and each one will produce dust clouds that temporarily affect the visible brightness. Some events might be even more dramatic than what we've seen so far, including possibly very large brightening events that produce false alarms about the supernova actually beginning. Distinguishing the real precursors from false alarms will be a challenge. The real warning will come from neutrinos, but until that signal arrives, every dramatic surface event will provoke speculation. Astronomers will need to be careful not to declare the supernova prematurely. The scientific community has learned from the 2019 experience that visible light fluctuations alone are not enough to predict an imminent explosion. Siwaha will continue to play a role in the final years. As the companion approaches its fate, the binary interaction will probably get more violent. The orbit may continue to decay. The wake patterns may evolve in complicated ways as Betelgeuse's atmosphere becomes more disturbed. There's even a possibility that the merger event, if it happens, could be visible from Earth as an unusual brightening that some observers might initially mistake for the supernova itself. The pulsation cycles may also change in the final stages. As the core moves through its remaining fuel stages, the conditions in the star's interior shift, which in turn affects how the outer layers respond. Different pulsation modes may become more or less prominent. New rhythms may emerge. The familiar 2,100-day cycle, dominated by Siwaha's orbit, may be supplemented or even replaced by other patterns as the system evolves. The star will also likely keep losing mass at increasing rates. Red supergiants near the end of their lives can shed significant material in the years before they explode. The lost material forms a circumstellar shell around the star, which interacts with the eventual supernova in interesting ways. By the time Betelgeuse explodes, it may be surrounded by a substantial amount of recently ejected material, and the supernova will plough through this material as it expands. The interaction would produce specific signatures that astronomers would catch in the early observations of the explosion. Watching all of this play out is the privilege of our generation. No previous generation has had the tools to study a red supergiant in this much detail in the lead up to its explosion. Future generations may witness the explosion itself, and they'll inherit our observations of the final years before. The records we are making right now will be foundational documents for the science of stellar death for centuries to come. When the moment finally arrives, it will probably catch even the most prepared observers off guard. The neutrino burst will trigger the alerts. The visible flash will follow within hours. The sky will change. Orion's right shoulder will blaze for months, then fade. A neutron star will be left at the centre, a cold gravestone marking where a giant once burned. We don't know when. We just know that somewhere out there, the countdown is running. And the next few decades may finally bring the moment we've all been waiting for.